Today we're going to focus on the precise definition of a limit. So far in class, we have talked about using limit laws and direct substitution, maybe some algebraic manipulations to arrive at a limit, but that is while we're working as we get closer and closer to some limit. But we need a precise definition for the limit that we can use all the time. So the precise definition of the limit is as such. Let f be a function defined on some open interval that contains the number a, except possibly at a itself. That's why it's an open interval. Then we say the limit of f of x as x approaches a is L, and we write it as you see here. If for every epsilon greater than 0, there's a number delta greater than 0, such that if the distance between x and a is small but positive, then the distance between the function and the limit has to be less than epsilon, which is an error tolerance. And so what we're trying to do here is we're trying to get super close to that a value so that our function can get very close to our limit. Now let me show you a visual of that. In this image, we have our function f of x, we have our limit L, and our value of a that we're trying to get x close to. And we're going to be trying to make sure that the distance between x and a is within delta. And so these lines that we've drawn with the yellow on the x-axis, that's a plus this value of delta and a minus this value of delta. The lines that we've drawn in red, that is your limit and the distance between that and the function. So down here would be the function minus the limit, and above we would have the function plus the limit. And what we're doing is we're trying to make those yellow bars closer and closer together and make those red bars come down as well, so those lines to try and zero in on this limit. Let's think about this algebraically. How can we relate these two things? Remember, we're talking here about x minus some a less than delta, and the function minus some limit being less than epsilon or error. Starting with our function, the absolute value, remember if I have the absolute value of x is less than a, that's saying the same thing as negative a is less than x is less than a. Let's use that idea to drop the absolute value in our function statement. This is the same thing as negative 0.4 being less than the square root of x minus 2 being less than 0.4. Adding 2 to all three pieces of the inequality, we get 1.6 is less than the square root of x is less than 2.4. Well, continuing to solve for x, if we square all three pieces, we get 2.56 is less than x is less than 5.76. Going back to our statement about delta, we can use that same idea of absolute value, and we know that x minus 4 has to be less than delta, has to be greater than negative delta, but if you add 4 to all three pieces of the inequality, we have negative delta plus 4 is less than x is less than delta plus 4. So let's compare the delta plus 4 to 5.76 and the negative delta plus 4 to get another value that might help us what delta would be. So delta plus 4 is 5.76. Then what does that mean that delta is? In that case, it would be 1.76. Negative delta plus 4 equal to 2.56 gives us a delta equal to 1.44. Now remember that this statement has to be true for all delta, so we want to go with the smaller delta because if we chose a bigger delta, it's not going to work for all values. So here, the value that's going to work for us is going to be 1.44. That means that if x minus 4 is less than 1.44, then the absolute value of the square root of x minus 2 is less than 0.4. Let's look at that on a graph image. Here is our graph of y equals the square root of x. And then we have our parameters where if we're talking about our delta, our a value is 4, our limit is 2. So the distance between 4 and delta has to be within 1.44 in order to capture that limit. Notice that these bands around x are not the same distance because we determined that one of them was 1.76 and one of them was 1.44. So if we shorten it to 1.44, we are still going to make sure that we have captured that limit. So that is a practical application using the formal definition of a limit. What happens if we don't have a graph and we need to, say, work with another function? Let's try that. You might be asked a variety of questions. You might be asked to find the delta value given a certain error tolerance, or find the limit and then find the appropriate delta. But you also might be asked to write an epsilon delta proof. Writing an epsilon delta proof can be difficult depending on the type of functions that you're dealing with. Now, if I wanted to do this with a function that's a polynomial, I could start out by determining what the appropriate delta should be first. This is considered scratch work, and if you're writing a formal proof, should not be included in your proof. But you need it to be able to determine what the appropriate delta is in order to write your proof. So it's kind of backwards. We work backwards to find the delta that's going to work to solve our proof. Let's take, for example, the limit as x approaches 4 of the function 2x minus 5. And I want to prove that that limit is 3. When I asked you before what the limit was, you would just plug in 4, you'd use direct substitution. But that's not proving it. We're going to prove it by making sure that if the distance between x and a is less than delta, then the distance between the function and the limit is less than epsilon. Where we start is to do the scratch work. We want to substitute in our values for a, our function, and our limit, and kind of compare the two to see what sort of scratch work we need to do in order to find our appropriate delta. Doing that, we have that our a is 4, our function is 2x minus 5, and our limit is 3. If 0 is less than the distance between x and 4 is less than delta, then 2x minus 5 minus 3 is less than epsilon. Right now, they don't really look like they compare well, or they're not similar. Let's keep going, do some simplification of the function. We get 2x minus 8 is less than epsilon. And now you might seem to recognize, oh, how does x minus 4 and 2x minus 8 look similar? I can factor out a 2 in the epsilon statement. And if I factor out a 2, I have x minus 4 is less than epsilon. And using properties of absolute value, I can actually take the 2 outside of the absolute value, because the absolute value of 2 is always going to be 2. And we have 2 times the absolute value of x minus 4 is less than epsilon. Well, notice that x minus 4 has to be less than delta. So I can go ahead and substitute in a delta here, and I would have 2 delta is less than epsilon. Solving for delta, we get delta should be less than epsilon over 2. So that's our choice for delta. Now we're actually going to use that in a proof. And in our proof, what we do is we start out by saying epsilon for every epsilon greater than 0. And then we do our math backwards to get back to what we've done in our scratch work. So if we're going to let epsilon be greater than 0, and we're going to choose delta equal to epsilon over 2. Then we start with our function and our limit statement. And we say then the function 2x minus 5 minus 3 is the same thing as, we're simplifying here just like we did before, which is the same thing as 2 times x minus 4, which is the same thing as 2 times the absolute value of x minus 4, which we know the absolute value of x minus 4 is less than delta. This statement here has to be less than delta, and we know that delta is epsilon over 2. So we have 2 times delta, which is epsilon over 2, or epsilon. So we have shown that the function minus the limit is less than epsilon. You could finish off your statement by saying, therefore, if 0 is less than the distance between x and 4, is less than delta, then our function minus our limit will be less than epsilon. Doing another more complex version of the delta epsilon, we'll take a polynomial that can be factored. Let's start with the limit as x approaches 2 of x squared plus 2x minus 7 equal to 1. We want to do our scratch work first. Identify your a, your f of x, and your L, and write it in the appropriate statement. That means that 0 is less than x minus 2, our a less than delta. And then our function, x squared plus 2x minus 7, minus our limit, is less than epsilon. Simplifying on the right-hand side, we get x squared plus 2x minus 8 is less than epsilon. Now remember, we're trying to get somewhere near the x minus 2 statement. Now factoring, we can get x minus 2, x plus 4 is less than epsilon. So we look like we're in business here. Separating those using the triangle inequality, we have the absolute value of x minus 2 times the absolute value of x plus 4 is less than epsilon. If we were following the same idea as before, we know that the absolute value of x minus 2 needs to be less than delta. So I could say delta, absolute value of x plus 4 is less than epsilon. So I need to just choose delta to be less than epsilon over the absolute value of x plus 4. But we can't do this. And the reason we can't do this is because our delta needs to be a constant and cannot be in terms of x. One thing we'll always use is it's reasonable to assume that the distance between x and a is within 1. So the absolute value of x minus 2 can be within a distance of 1. Splitting that into negative 1 is less than x minus 2 is less than 1. And solving for x, we get 1 is less than x is less than 3. So x needs to be between 1 and 3. Well, what sort of implications does that have for the absolute value of x plus 4? Well, if x was 1, 1 plus 4 is 5. And if x was 3, 3 plus 4 is 7. Now we have the fact that the absolute value of x plus 4 has to be less than 7. We can go back to our statement where we had x plus 4 absolute value, x plus x minus 2 absolute value had to be less than epsilon. We know that x plus 4 has to be less than 7. That gives us 7 absolute value of x minus 2 is less than epsilon. Solving for the absolute value of x minus 2, we know that that now needs to be less than epsilon over 7. We want our restrictions. Remember, we've said that the absolute value of x minus 2 has to be less than 1, and it also needs to be less than epsilon over 7. But we have to have delta be the smallest so that it works for everything. So we want delta to be equal to the minimum of either 1 or epsilon over 7, whichever one is smaller. Now we have the tools we need to go ahead and solve this proof. We're going to let epsilon be greater than 0, and we're going to choose delta to be equal to the minimum of 1 and epsilon over 7. And then remember, we start with the function and the limit. So then recall that the absolute value of the limit, x squared plus 2x minus 7 minus the limit, is equal to, in factored form, x plus 4, x minus 2. And recall now, we can say that the absolute value of x minus 2 has to be less than epsilon over 7 at this point. So we have x plus 4 and epsilon over 7. But remember that earlier we said that x plus 4 absolute value has to be less than 7. So now that's equal to 7 times epsilon over 7, or epsilon. Then we can say, therefore, the limit was equal to 1. This is an example of a more difficult epsilon delta proof that requires you to consider constants and minimums and do a little bit more math. I look forward to hearing your questions in our next class.